screen. Please acknowledge if my screen is visible. Is my screen visible?
Yes, sir.
Okay, and I hope my audio is coming clearly. I'm
Yes, sir.
audible
You are,
properly.
you
Okay.
are audible, sir.
Okay, so hi guys. We might be like you might be attending my session for the first time. My name is Purvang Mantri. Yeah, as Sir said, I am a YouTuber, and adding on top of it, I am an educator and an author. So in today's session, we are going to talk about electricals, electronics, and its innovations. So we are going to look into the basics of control system, what a control system is, what kind of mechanical control systems which are already being used in our vehicles, which you might have, which you might be knowing at this point, but you don't know that it is termed as a control system. So we are going to look into those kind of mechanical control systems. Then we will look into what kind of electronic control systems are used in our vehicles. Then we are going to go further deep into the basics of the control system and see how control systems are made, like what kind of parts are used to make a control system. And for that, first and foremost, we have electronic switches. In electronic switches, we are going to talk about bipolar junction transistor, metal oxide semiconductor field effect transistor, insulated gate bipolar transistor. And then we are going to look into analog signal, digital signals, ADC converters, DAC converters, because these are all these five parts, like electronic switches, ADCs, and DAC converters are used in microcontrollers. So they are integrated over that particular chip with the IC, and they are the brain of the control system which are used in our vehicles. If you want to call the microcontroller as ECU, it's entirely okay. ECU can also be termed as ECM, electronic control unit, or electronic control module. In many cases, we might have heard about engine control unit or engine control module when it comes to vehicle maintenance part of the thing. So similar, the function of engine control unit and ECU as electronic control unit is similar, but there are multiple ECUs, electronic control units, mounted in our vehicles that are controlling different parts of our vehicles. So engine control unit will only function for engines. Then there is body control unit, which functions for body, the passenger compartment, and then there is another infotainment control system unit, which controls your media and navigation and everything. Okay, so first and foremost, a control system is a system which provides desired response by controlling the output. So a simple example for a control system is a fan, or ceiling mounted fan. So if you want to have air around you, if you're feeling hot, if you're feeling warm, but you want to chill down the room, you want to reduce the temperature of the room, you're going to switch the fan on, right? That's the basic thing which we are going to do. So that is a typical form of control system. Also, specifically speaking, it is one of the open loop control system. So you just press the switch and you turn the fan on. And if you want to control the speed, you turn the regulator in clockwise or anti-clockwise direction, which controls its speed. So that's a basic form of control system. Adding on top of it, we have one closed loop type control system which has a feedback loop. I'm going to grab a pointer, a pen. So in feedback loop, we have sensors on the output shaft or on the output of whatever the control system is handling. So that output is going to be transformed into a transform function. I'm not going to go deep into this transform function because it contains Laplace transform and Z transform, and you're going to. I know we don't want maths anywhere around us. So this is where Laplace and Z transform is implemented. Okay. So the like for example, if you're talking about fan, so we can have a tachometer mounted with the shaft of the fan or the rotor portion of the fan. So that tachometer will give the readings of the speed of the fan to the microcontroller back. So microcontroller will compare the input, like what input we provided. So we wanted it to be running on full speed, but certainly the tachometer is saying that it is not running on full speed. It is running on a half speed or slightly more than it. So with this tachometer or with this sensor, the microcontroller will come to know that there is a error in the output and the input. It will correct that out. It will correct that error and increase the speed of the fan. So that this is a closed loop type control system. Like let's talk about what kind of mechanical control system which we are already aware about. First and foremost, on the left side, you can see this is a governor. You might have studied about governor in your second year in theory of machines or kinematic of machines. I hope you have. Please Please confirm that you have studied governors. Okay, no one is answering. I'm assuming you have, but still, I'm going to give you a brief explanation about this. So, this is a speed control governor. It has flyweights on the end, and it is mounted on a shaft, a rotating shaft. So, as the speed of the shaft increases, the flyweight will fly out because of the centrifugal force. And as these flyweights will fly out, it will pull this middle section upwards and disconnect the shaft. So it will control the output speed of the shaft. If it exceeds a certain limit, it will disconnect the shaft and it will prevent the speed of the output shaft to be more than what is desired. So this is a speed governing speed control governor. It controls the speed of the output shaft. Then similarly, we have steering system. Steering system is of course a type of a mechanical control system because the driver is turning the steering wheel, which in turn turns the front wheels in certain degrees. Now, if you have ever paid attention while driving your car, then you would have noticed that you are turning the steering wheel for almost 3 turns. Like if the wheels were pointing in the left direction, and then then you want to turn the wheels to the right in the right direction, then you have to turn the steering wheel for almost 3 turns, three entire turns in clockwise direction. And for that entire three turns, the front wheels will only move for certain degrees, barely 45 degrees from left to right. So for 3 turns, you can control like the degree of the steering wheel, and the front wheels can be multiplied or divided into certain angles. So that is a type of control system. Similarly, we have an hydraulic control system, which is a braking system. So in automotive braking system, we have a master cylinder, we have a combination valve, which is the distribution valve, which distributes the fluid to front and the rear axles or the rear brakes. Then we have the front brakes, which are disc brakes. Then we have rear brakes, which are the drum brakes. So when the driver presses the brake pedal, the because of the Pascal's law, the pressure applied on any stationary fluid will be divided in equally in all directions. So based on that, this automotive braking system will uh, transmit the pressure of the brake to all four wheels equally. And it is again a type of a mechanical control system, because hydraulics is a part of mechanical engineering. Okay. So similarly, we have some electronic control systems. Now this particular diagram, one on left, this diagram is for ABS, anti-lock braking system, EBD, electronic brake distribution system, brake force distribution system, traction control, TC, and electronic stability control, ESC. So all four systems work hand in hand. The microcontroller is same. The sensors used in those in all four safety aspects are same. Their output is also almost same. Okay, so in this we have sensors on each wheel, which the speed sensors on each wheel, which actually measures the speed of the wheel. And if there is any difference in the speed of any wheel, so the microcontroller is going to compare speed of all four wheels versus the speed of the vehicle. So if there is any difference in the speed of any wheel, the microcontroller has the ability to press brake on one individual wheel or two wheels of whatever the desired output is required for maintaining the safety of the vehicle. Okay. Similarly, we have on the right side, you can see this is a schematic diagram for throttle by wire, or you might be knowing about you might be aware about ride by wire or drive by wire system. So in our mechanical systems, like the in our low budget commuter motorcycles, or for example Splendor, Passion, even Royal Enfields, many Royal Enfields, they have cables to control the throttle. So your throttle accelerator on the handlebar has cables in it. Those cables are mounted with the carburetor throttle valve. In today's time, we don't use carburetor, we use electronic fuel injection system. So the throttle valve is directly connected with the mechanical cables or mechanical linkages. So as we rotate the accelerator, the cables will pull or push the throttle valve open or close it, or in closed direction. Okay. So this entire mechanical system can be replaced by an electronic system, where there is a position sensor on the throttle. Then there is a microcontroller which senses the position of the throttle, which gets the data of that position of the throttle, and based on that data, there is a servo motor connected on the output end of the microcontroller, and that servo motor is mounted with the throttle valve. This is the throttle valve. So as you press the throttle pedal, the position sensor is going to give data to the microcontroller, and it is going to signal the servo motor to rotate in that particular direction. This might be difficult to imagine at this point. So don't worry. I have created a small what we call it simulation for you guys to understand. I have created a potential. I have attached a potentiometer with an Arduino, and it controls the servo motor. So I'm gonna show it to you how this kind of system works. Okay. So this is the figure below is just the parts which are showing, which are being shown. So this is the throttle pedal, this is the ECU or the ECM, and this is the servo motor and throttle body assembly. Okay, the servo motor is mounted over here. This is the throttle body. So what makes a control system possible? So why are we, how is it, how can we make a control system, and what gave us the ability to make a control system? So it was because of semiconductors. You must be aware about that. We are like the current scenario of our world is that we are lacking in the department of semiconductors. There is a lack of semiconductors, and during 2020 and 2021, year 2020 and 2021, Bosch had reduced like they had reduced their production facility of producing their ECUs. This was because of lack of semiconductors. So can anyone come forward and give like define what semiconductor is? Yeah, students, can any one of you answer what semiconductor is, or what are the characteristics of semiconductors?
Semiconductor, silicon is the semiconductor.
Okay, yeah, that is correct. But what defines silicon to be a semiconductor? What is the definition of semiconductors? So okay, so can you define what conductors and insulators are?
Sir, conductors which are conduct electricity,
Okay,
heats,
yeah,
and insulator are opposite to that.
okay, yeah. So
And which
conductors.
lies between both of them, this is semiconductor.
Yeah, exactly. That is correct. So semiconductor is a material that is basically an insulator, but can also act as a conductor when it is given some energy. So I don't know if you guys have learnt about this band theory. So this band theory defines like what kind of energy is required to make any substance or make any element into a conductor. So conductors usually require very little energy to have it conduct electricity. We are going to talk specifically about electricity over here. Let's keep heat aside. We don't want to talk about heat at this moment. Okay. So to make aluminium, iron, or copper, silver, gold, platinum, or any of these metal conduct electricity, it requires very less energy. Okay. But when it comes to insulators like rubber, wood, plastic, and ebonite, so these are bad conductors. They are insulators because they have the ability to resist electricity. They can be made into a conductor. Now, okay, for someone please answer me, is air air हवा हमारी आजू बाजू की हवा, is it a conductor or is it an insulator?
Insulator.
But if you pay attention properly, yeah, the answer is correct. Yeah, it is an insulator. But whenever the lightning is stuck from sky to ground, whenever there is a thunderstorm, and when there is lightning, that lightning is passing through air. That means air is conducting electricity, right?
Yes, sir.
Yeah, but if we are on the other end of that lightning, we are going to get burnt, right? We are going to die instantly. Am I correct?
Yes, sir.
Yeah, okay, good. So yeah, I would like to say air is a semiconductor. I mean, no, not a semiconductor. Yes, basically it is an insulator, and it requires a lot of energy to get ionized. Ionization is the process in which the electricity passes through air. Okay, so if we ever had the chance to, you can also Google how much voltage any lightning has, and that is way too much. We won't even survive even if we if we even point our fingers towards that lightning, and if it gets attracted towards us, we are gonna get we are going to turn into ashes in millisecond. Okay, so that much amount of energy is required to make an insulator a conductor. So an insulator can become a conductor, but it requires tremendous amount of energy. because there are like there is a valence bond. I hope you guys are aware about valence electron. If you are not, no worries. The next slide is going to be about valence electrons. So similarly, semiconductors lie somewhere between insulators and conductors. They in typically in nature they are insulators. Like if you have ever touched silicon, even our glue, eraldite glue and like hot glue, okay, the glue which you apply with that glue gun, right? So that is a form of semiconductor because you are using silicon. Okay, even certain molds which are used in bakery items like for making cake or anything, lasagna or cake something. So those are those flexible molds are actually made of silicon. But when you apply electricity to it, nothing is going to happen. Am I correct? Yeah, can someone answer me? If you apply, like you have used silicon, there is like you might have silicon around you lying right now. Okay, so in like silicon in pure nature is an insulator. It becomes semiconductor when we add something to it. I'm going to talk about what we add. So first and foremost, let's talk about valence electrons or valence band. So valence electrons are those electrons which are in the outermost orbit of an atom. Okay, now just so you know, we might be going back to our 11 12 to the syllabus of our 11 12 to brush your brain, like to brush up your memory for these concepts, because if you are aware about this, if this is planted in your head, then you would understand electronics very easily. Okay, so valence electrons are the electrons which are in the outermost orbit of an atom. Okay, and it can be determined like based on how many atoms are there. Like hydrogen has only one atom, I'm sorry, one electron in its outermost orbit. So it means like, or in its first orbit, it only has one orbit, right? Hydrogen has only one orbit. So in its first orbit, there is only one electron. But to fill that orbit, in total, it requires two electrons. Okay, so the, hydrogen in just hydrogen is its first and last orbit is incomplete, and that's why it has a valency of 1, because it lacks one electron in its first or last orbit. Similarly, carbon has a valency of 4, oxygen has a valency of 2. Now I know you must be aware about the positives and the negative signs of valency as well. I am not going to go back there. I'm just brushing your knowledge about valence electron at this point. Similarly, metals like silicon and germanium, elements like silicon and germanium also have valency of 4. But silicon and germanium both are semiconductors, yet they don't conduct electricity even if it is given some energy. It is because of the impurities that we add into it that allows them to conduct electricity. Okay, this method is known as doping. To understand doping, I would ask you again, is water an insulator or conductor? Yes, guys, is pure water, pure H2O, is it an insulator or a conductor?
Insulator.
Yeah, exactly. So if you want to convert it into a conductor, you need to add table salt or NaCl, sodium chloride, right? I hope you are aware about this, right? If you add salt in water, it becomes a conductor. It starts conducting electricity.
Yes,
If
sir.
yeah, so after adding water and plugging the two ends of a battery in that dilute solution of water and NaCl, if you put a finger in it, you are going to get you are going to feel a shock. Okay, I had feel a shock, so that's why I'm talking about this. So this adding of salt in pure water is the method of doping. Doping is adding impurities, and which makes the semiconductors act as a conductor. So similarly, silicon can become a conductor by adding impurities like arsenic or gallium. Even you can also add boron. You can also add uh, I don't remember the other names right now, but arsenic, gallium, borons are like impurities that needs to be added into silicon or gallium so that it makes into a conductor. So in this case, look, silicon has a valency of 4. You can see it over here, and arsenic has a valency of 5. These electrons are of arsenic. Okay, so when silicon and arsenic are mixed together, they create 4 covalent bonds. So like arsenic creates covalent bond with silicons all around it, and because of this, one electron remains out. As arsenic has 5 electrons in its last orbit, 4 electrons are going to get bonded with silicon atoms, while the last electron, the 5th electron, is going to be free. It will not bond with anything. So it becomes a free electron. Okay. Now, if you remember the definition of electricity or electric current is defined as the flow of electrons. So it is typically the flow of these free electrons that is current. Okay. So this type of chemical bond of silicon and arsenic is known as p-type semiconductor. I'm sorry, n-type semiconductor, because it is giving away a free electron. Okay. While in case of gallium has a valency of 3, which means it has 3 electrons in its outermost orbit. So it creates bonds with 3 silicon atoms, but the 4th silicon atom is going to remain without, like, it is not going to bond with gallium. So because of this, there will be a hole created over here. Hole is nothing but a positive charge of the semiconductor, and because of this hole, this kind of bond is going to be known as, or this kind of semiconductor is known as p-type semiconductor. So this hole will attract electrons. This hole will attract electrons from other, like with other parts, like which will allow the electricity to flow through it. So by adding impurities, you can make semiconductors will actually become conductors. Okay. I hope you are clear with the method of doping. Please say yes or no.
Yes, sir.
Okay, good. So, using this impurities and semiconductors, we have the invention of electronic switches was possible. And electronic switches are nothing but regular switches, but they are operated using electricity. Like we have switches for a fan and air conditioners and various sockets, right? So those switches are operated manually by us. But in case of electronic switches, those switches are operated electrically using electronic signals or electrical signals. Those electronic signals are given by microcontrollers. Okay. So we have many types of electronic switches. Basically, they are transistors, but they have different names based on their construction, or based on their polarity, or based on their material used. Okay. So first and foremost, we have BJT, also known as bipolar junction transistor. So the name bipolar is because this type of transistor can have two different polarities based on how the material is used. So it can be an N-type transistor or it can be a P-type transistor. So this first image is showing the P-type transistor, while the second image is showing an N-type transistor. So this type of transistor or electronics which is controlled by current. So when the base, so it has 3 terminals: emitter, base, and collector. So when base is given a reverse current, it will allow the electricity to flow from emitter to through collector. Okay, so it technically is acting as a switch. So these diagrams would be difficult to understand, would be difficult to remember, but to understand its function, I would just tell you guys to think of a solenoid. So let's assume like this is a metal strip. We have supply over here. Okay. And let's put a ground over here. Okay. And here is some load. There's some resistance or load over on the output end. Okay. And we are placing a solenoid. This solenoid is controlled electronically. Okay. So what happens when the solenoid gets electricity? It gets charged up, and because this is a metal strip, it is going to get attracted towards it. Okay, it is made of iron, so it is going to get attracted towards the solenoid, and it will close the gap, and thus it will allow the electricity to pass from battery to the load. Okay, so this is a typical understanding of a transistor, like a basic understanding of transistor. No one is going to tell you this is the correct way, but to understand it, because I am coming from your background, and it was difficult for me to understand transistor in this way, in the way what other faculties or other colleges show. So to make it easier for you guys, I'm gonna like tune it down on a lower level so that it becomes easy. Okay, so this is a typical understanding of any electronic switch. So consider base as a solenoid. Never say it is a solenoid. It is just for understanding. Okay. So similarly, we have MOSFET, or metal oxide semiconductor field effect transistor. Even this has 3 parts. It instead of emitter, base, and collector, it has gate, drain, and source. Only the names are changing, the functionality is same. The difference is that MOSFET has fast recovery time and fast switching time. So like the frequency of switching the drain on and off can be fast, it can be speedily done in a MOSFET, while in BJT it takes slightly more than slightly, like it is slightly slower than MOSFET. Okay, so these are MOSFETs are highly preferable in high frequency applications like in our audio systems or internet or anywhere. Okay, wherever there is high frequency networks. Okay, so this was a basic understanding of any transistor or any type of electronic switches. To make it even clearer, to make the picture even clear, let's take this particular diagram. I'm going to draw it over here so it makes clear to you how electricity passes through it. And there is a reason why I took the idea of what we call it, this solenoid. So this is source. We have gate over here. I'm going to just draw gate at bottom, and then there is drain. Okay. So what happens is gate is below gate here. There is another like what we call it, semiconductor. So if it is NPN, so it this will be the n-type semiconductor on both ends, and there will be a p-type semiconductor on this end. Or else if it is a PNP, so according to that, so PNP and NPN was this one. Okay, this is an n-type transistor or n-type semiconductor, and this is a p-type semiconductor. Okay, so when we apply current to the gate, what happens is, so free electrons are going to be present over here on both ends. Okay, on both n and p-type semiconductors, but as they will be free and they won't have any sort of orientation. At this point, they are not conducting electricity, but when we apply some energy to it, when we apply energy to gate, these electrons are going to be going to get attracted towards this end on this one surface, because of which it creates a bridge. Okay, it creates a bridge, and thus the electricity is going to flow from source to drain. So that's how almost every transistor or electronic switch works. This is the proper explanation for the functioning of any electronic switches. The only difference is they have different names. There is BJT, there is MOSFET, there is IGBT, there is transistors. Okay, but and now MOSFETs. But to understand like what advantages or disadvantages what with like each electronic switch has, that's what we have to learn. That's what we have to memorize. So MOSFETs have fast switching time, and it can be turned off quickly as well, and thus it is highly preferable in high frequency applications. Then lastly, we have IGBTs, which are insulated gate bipolar transistor. Again, bipolar, this can be N-type or P-type, I mean NPN and PNP transistors. So it is a combination of BJT and MOSFET, bipolar junction transistors, and metal oxide semiconductor field effect transistor. Okay, so it takes the fast switching speed of MOSFET, while it takes the while it can handle large output current as BJT, and it can be controlled by voltage or current. So you can apply voltage or current to the collector, and thus gate and emitter will switch on or switch off. Okay, I hope you understand how electronic switches are working. I hope you understand the working of electronic switches by now. Yeah, guys, yeah, please answer with yes or no. I hope you understand understood the working of electronic switches.
Yes, sir.
Yeah, good. So next thing we have are analog and digital signals. Now, analog signals are nothing but frequency with respect to time, or amplitude with respect to time. It is the change in the value of any quantity, like for example, audio signals, voltage or pressure. So voltage, like to draw, if you ever draw voltage, let's say it is an alternating current or AC current. So the voltage values are going to go positive and then negative and then positive. So it has some amplitude and it has a frequency. Okay, and a wavelength. So this is an analog signal. It is a signal between 0 volts to 2.5 volts, or say 5 volts, and it goes back to 0 and then it again rises. So this is an analog signal. Then like they change with respect to time. Then there are discrete signals, or also known as digital signals. These are, in typical term, they are just ones and zeros, which means they are binary or logical signals. But technically, they are electrical signals as well. Okay, so a zero bit or a zero, like a zero binary digit or a discrete value, is going to have a zero voltage. But if you want to give it, like if you want to have 1 byte, okay, it will have 5 volts. So the microcontroller will give digital signals by controlling the voltage for certain time. So if, let's say, for if it is like you guys have heard about this term called speed, CPU speed or CPU frequency. Like for example, when you're buying any piece, any laptop or a processor for your desktop, you would be looking after the CPU speed, and it would be written 3.3 gigahertz, which means it can send, or it can shift from it can send 3.3 these signals with 3.3 gigahertz speed. Gigahertz is the speed of its frequency. Okay, so it can shift from 0 and 1 to 0, 0 and 1 in that much amount of time. It can be that fast. So similarly, microcontroller, this might look like a square graph or something, but it is nothing but voltage. So this one is going to be defined as 5 volts for a certain time. Let's say 1 second. For 1 second is quite large time, large amount of time. But let's say, for example, for a second, if the voltage is zero, the controller is going to take the binary digit as zero. But as soon as it rises up to 5 volts, it is going to consider it as a one. Then it also again drops to 0 volts. So it registers it at 0, 0, and then 1. So similarly, by shifting between voltages with respect to time, it's defined in binary signals. Okay, I hope you understood digital and analog signals as well.
Yes, sir.
Okay, so these are the basics of electronics up till now. Then we have like to convert analog signals into digital signals. We use gate or comparators. So this is a typical diagram or a schematic diagram for an analog to digital converter. So if you want to convert your analog signals into digital signals, you need to have ADCs. And there are DACs, digital to analog converters, which convert digital signals into analog output. So to understand this, we have comparators mounted on the input side. There are multiple comparators, and they have a reference value. So this particular line shows the reference values. So one terminal of the comparator is connected to the reference values, which can be 3 volts, 2 volts, or 1 volt, or maybe 0 volts. Okay, we don't have anything for 0 volts. 0 volt is just filtered out. Then we have the analog signal, which is the input. So the signals would be something like this. Okay, the values are going to change continuously. So these signals are compared. These are voltage signals. Okay, these are voltage signals. They have peak, they have crest, and these signals are given to the comparator. So comparator compares the signals with the reference, like the voltage signals with the reference voltage. So let's say, for example, if a signal, like this is the first signal which is coming through here, and it has a voltage of 4 volts. So when 4 volts come in, it is going to get compared over here, and it is going to be filtered, and thus it is going to register as 1 bit. Okay, but let's say it goes down to almost 1 volt. So 1 volt is going to get filtered out, like it is less than 2 volts, so it is going to get filtered out. It is going to go down, and the 1 volt comparator is going to compare it with the reference voltage, and thus the encoder will reduce its what we call this digital signal, a binary digit, into zero. So similarly, it compares it. It is like coin slotting machine. It slots the coin for its diameter. I hope you understood this analogy, right?
Yes, sir.
Yeah, good. So similarly, we have DACs, or digital to analog converters. So they convert digital signals into analog converters. So at times, if you ever had the chance to see the output of any motor controller, then their output is going to be a digital output. It will have such a form of square waves, and both rising and falling. So it has certain values. So it will be 0 volts, 1 volt, 3 volt, 5 volts, 7 volts. This is just an example. So this is not a proper smooth wave like this, like any alternating current. It is a form of square wave, and it is discrete with time. Each voltage value is present in the conductor for a discrete time. So that's why it is known as digital signals. So these signals are going to be given to the encoder in the similar fashion, and this encoder, based on its voltage values, it is going to convert it in the form of an analog voltage signal. I hope you're clear with this.
Yes, sir.
Good. So both these analog and digital converters, like ADCs and DACs, are mounted in microcontrollers, and microcontroller uses both these type of converters to give the desired output. So let's now talk about components of electronic control systems. So every electronic control system will have three basic parts: sensors, microcontrollers, and actuators. So to understand sensors, I would like to like you guys to think of our senses, our five senses: eyes, like the sense of vision, speaking, hearing, feeling, and taste. So these are all the sensors we have. Eyes is a sensor; it is our camera, right? My mouth, the way I'm speaking, it is my speaker. Okay, my ears, they are the microphone. They are picking up audio signals. Then our skin, it is a type of proximity sensor. It can feel if the temperature is rising, if anything is hot or cold, or if you touch anything. Okay. Similarly, we have our tongue. It can bifurcate the taste. It can sense if anything is spicy or anything is sour, bitter, or salty. Okay, so we have five senses. Similarly, from these senses, we develop various sensors like humidity sensor, temperature sensor, ultrasonic sensor, laser sensor, lidar sensor, alcohol sensor, potentiometer, photoresistor, rain sensor, and there are many more sensors like this. Okay, so these sensors, there is they have the ability to change the resistance for the required, like for whatever quantity they are designed for. Like for example, a light sensor will have its resistance change based on how much light is embedded on it. Okay, like then similarly, we have humidity sensor. Humidity sensors resistance will change if the humidity of the atmosphere rises or falls. Then we have accelerometer, which is nothing but a gyroscope. Like for instance, it is a type of gyroscope or a gyro sensor. Okay, gyro sensors and accelerometers both are defined differently, but their functioning is almost same. Accelerometer will sense the change in speed. Okay, so sensors have the ability to change the resistors for whatever quantity it is designed for, and the output and the input. So, if there is a resistance, if it is increasing and decreasing with time, it needs to have, like, if you want to measure that resistance, you need to have voltage applied to it. Okay, so if this is a varying resistor, and we know that we are giving it 5 volts, if it is getting reduced, we know that this resistance increase. So the amount of the change in this resistors has like there are formulas that have been already developed, so that we already know that for this much change, for this much voltage, that this is the output value. Like for example, if it is a temperature sensor, if the temperature rises, its resistance is going to reduce. If the temperature falls, if it becomes colder, its resistance is going to increase. So if it is in colder region, if it is in the like chilled out region, the highest resistance is going to be applied over this circuit, and 5 volts is going to reduce down to 0 volts. So the microcontroller will come to know that if there is no output, it means the temperature outside is cold. But if it is hotter, if the temperature sensor is placed in a warmer conditions, the resistance is going to be least, almost near to zero. So 5 volts will go just flow through them, and the output value would be 5 volts. So the microcontroller will know that as the output values is 5 volts, that hot. Okay. So this is the basic understanding of sensors. Then microcontrollers are our brain. Like in proper analogy, it is our brain. So our brains, like the sensors from our five senses, is sent to our nervous system or our brain, and it, based on that data, it decides a particular output. Like for example, and to understand actuators are our muscles. Because like actuators allow us to move our arms, so our muscles are our actuators. Our human body's actuator. We have various types of actuators. There are mechanical type, there are pneumatic type, there are hydraulic type. Okay, so based on the data of sensor, the microcontroller decides the output or the signals for actuator. Uh, if the like for a certain value of input, it will provide a certain output. Okay. So let's look deeper into all the types of sensors. First and foremost, we have potentiometer. Potentiometer is nothing but your fans regulator. Okay, so you rotate your fans regulator in clockwise or anti-clockwise direction, and the speed of your fan changes, right? So that regulator is nothing but a potentiometer. So potentiometer has a resistive strip or a resistive track. Where is my okay? So this is the basic diagram of a potentiometer. There are three pins. One is input. Third one is output. I mean the ground. This is ground. Third, and this is output. Okay, so this wiper is attached with this knob which you can rotate, and this wiper is connected to a resistive track. This is a resistance over here. So when you rotate this knob, this wiper is going to rotate. So if this wiper is at the very bottom near the first terminal, so the least amount of resistance is going to act on it, and the electricity is directly going to flow through one and then out of two. Okay, so the least resistance is going to come. So if there is 5 volts coming in, 5 volts are going to go out. Thus, the potentiometer data or the reading is going to be 0. But as you increase this, if you rotate this, if it goes near 3, the maximum resistance is going to act on that 5 volts, which is going to flow through this entire circuit, and thus the output value is going to be 0. So by rotating the knob of potentiometer, the output voltage can be high or low. Okay, so this construction of potentiometer was taken into consideration for designing throttle valve sensor or even throttle sensor and a fuel gauge or the fuel sensor. Okay, so in our throttle valve as well, if you just rotate this in sideways and place it right like this, and here's the knob, you can see that it looks like a throttle valve of a bike. Okay, you can like you are holding this. Just assume that you are holding this and you are rotating it in clockwise or anti-clockwise direction, which is in turn going to turn the servo motor of the throttle body. Okay, so that's how potentiometer functions. Similarly, we have Hall effect sensor. Now, in Hall effect sensor changes, like the resistance of any Hall effect sensor changes when a magnetic field is acted around it. So this block over here is showing a Hall effect sensor, and at first let's assume the magnet is not near it, so it will allow the electricity to flow through it without any resistance. Okay, but as soon as we bring a magnet near it, it will attract the positive and negative ions on other ends, and thus it will increase its resistance. So as the resistance is going to increase, the input current or voltage is going to get reduced at the output, and by measuring this change in voltage, we can assume that if there was a magnet nearby or not. Okay, so this type of sensor is used in positioning or speed sensors. So our ABS sensor, many mechanics would have told you that your ABS sensor needs to be changed. They technically are changing the Hall effect sensor. So Hall effect sensor is used for measuring the speed of our wheels or speed of any shaft. It can also be used as knock sensors, and it is used as camshaft position sensor, crankshaft position sensor, and it can also be used as our this steering sensor as well. Most of the time for steering and throttle we use potentiometer, but wherever there is rotating parts and wherever there is a need to measure the speed of anything, we use Hall effect sensor. So then we have wave propagation sensors. So wave propagation sensors are these type of sensors that send a particular audio signal, a particular frequency signal, and it gets reflected back. And thus, uh, based on the time of sending the signal and then receiving it, they they measure the distance of anything ahead or around it. So these are known as wave propagation sensors. So there are lidar sensors, radar sensors, uh, we have ultrasonic sensors, and we have imaging sensors. So for long range, we use LiDAR. So this radar. So for these, for the one, this is the long range sensor. This showcases a radar sensor. It has a speed of like the speed of the frequency of those radar signals is 77 hertz gigahertz. Then we have near range infrared signals, which allows for night vision. Then we have near like short distance uh, night vision sensors, which uses cameras. Then we have ultrasonic sensors around our cars, which is used for our reverse parking sensors, and then we have finally ultrasounds or the ultrasonic sensors, which are mounted on the bumpers, which alerts the driver if anything is near our car. Okay, so there are three types of sensors. One is typical electrical resistance sensor, which is nothing but potentiometer. Then we have magnetically activated sensors, which are Hall effect sensors. And lastly, we have wave propagation sensors, which measures the distance. Okay, now we have microcontrollers. So one basic example of a microcontroller is our Arduino Uno. It uses Atomega 328. This block is the Atomega 328 chip. Okay. Now this microcontroller has pins on both ends. These are the input output pins. Okay. These are all like till here. These are all the input pins because we need to give it 5 volts or 3 volts based on whatever we are using it for, and we need to specify the ground as well. Okay. Then this analog in, these are A0 to A5. These are all analog input pins. Like the voltage values go in here. They register the analog signals. Then on the other hand, we have other digital pins, and out of which the ones which are marked with this kind of symbol, they are the PWM terminals. PWM is pulse width modulation terminals. PWM. You can see it like this here. You can see it is written as PWM. I'm gonna use the magnifying glass for you to for your visibility. Okay, so you can see these are all the digital pins. They give the output in ones and zeros, and their pulse width can be modulated, and thus they are also known as the PWM switches. Okay, so its operating voltage is between 1.8 to 5.5 volts. Its operating speed is, or the frequency is 20 megahertz. And there are almost total 23 input output pins. These pins are counted as the input output pins. And it has a memory of 32 KB, SRAM of 22 KB, and 1 KB. These specs are it doesn't matter if you know them or not, but you just need to know how it is constructed and what kind of pins to use for what purpose. Okay, so then we have SPC5. This is a standardized microcontroller for the application of for applications in automobiles or vehicles. So it has, apart from like this is a basic like, for a small scale model projects, Arduino is highly preferable. But when it comes to implementing microcontrollers or electronics in our vehicles, for we need to use microcontrollers which are AEC Q100 standardized. Okay, so this type of microcontrollers can operate in very cold and hot temperatures. Like for this one, this SPC5 can operate from temperature minus 40 degrees to 165 degrees Celsius. Okay, so it like you can understand like we don't like there are times when the certain parts get warm. For example, our engines are very warm, so we need to have microcontrollers that can withstand at that particular temperature. Simultaneously, it has certain communication protocols already implemented in them, like CAN, FD, Ethernet, LIN, and FlexRay. CAN bus protocol is highly used in our vehicles for communicating between microcontrollers. So as you might be aware that there are various ECUs around our cars. So one ECU would only be managing engine speed, other will be managing the what we call it HVC system or the AC system. So there will be one switch or one microcontroller just to operate our windows, the power windows. There will be a microcontroller just for power steering, one for ABS, traction control, ECS, and EVD. So all of these microcontroller can communicate with each other using CAN bus protocol and LIN bus protocol. LIN. Okay, CAN is for controller area network. If ever we get a chance to talk about just in-vehicle communication, then we can talk about all four of these communication protocols which are used in our vehicles and their advantages and disadvantages, and which one is highly used in our commuter vehicles, which one are used in luxury vehicles. So we can discuss it in that session if we ever have that session scheduled only. Okay, so we need to select, if you're actually making a control system for automobiles, then you need to select a microcontroller which is AEC Q100 compliant. Okay, so that's all for controllers or microcontrollers. Now let's talk about actuators, the muscles of our control system. So in actuators, we have servo motor. So servo motor is nothing but a simple electric motor. It can be like it gets controlled using a servo mechanism. So at times there are gears with it. At if you are using a different type of servo motor, then it will have teeth on it. Like there are two types of servo motors. One specific this gear type. The other is stepper type. So stepper motors will have multiple this what we call them the stator poles, and there will be multiple rotor poles. If you are aware about the design of an electric motor, there is a stator and a rotor. In typical electric motor, there will be either 2 poles, 4 poles, or 6 poles in the stator portion. And similarly, in rotor, it will have only 2, 4, or 6 poles. Okay, so these poles are the ones that allows the copper wires to be wound around it. So in stepper motor, there are more than 50 to 60 poles. They are small poles, but by controlling the electricity in each of these poles, the stepper motor can be rotated for a certain degrees only. Similarly, the servo motors can be controlled for a certain degrees only. Okay, so this can be controlled either with an alternating current or a DC current, or it can be or certain servo motors uses PWM. So what I was talking about here, pulse width modulation. So certain servo motors can be controlled using PWM signals. So PWM signals are nothing but digital signals, but the pulse width can be modulated. Like for example, if you want a servo motor to rotate for let's say 15 degrees, so the microcontroller knows that for 15 degrees you need to provide the signal for certain duration of time. So for 15 degrees it will give the signal for 2 seconds. Let's say this is 2 seconds. Now let's say you have set the microcontroller or ask the microcontroller to make the servo motor to rotate for 90 degrees. So it knows that for 90 degrees it needs to give the pulse, like the digital signal, for 5 seconds. So by modulating this width, this is the width and this is the pulse. Okay, this is the pulse and this is the width. So by modulating or controlling this width, the servo motors, the rotation can be controlled. Okay. Then similarly, we have hydraulic or pneumatic actuators. It is nothing but a piston cylinder assembly. And by injecting hydraulic fluid or compressed air, the position of the piston can be controlled. So these are the basic type of actuators that are used in our vehicles. If you are aware about our power steering systems, so power steering system might be, if it is electronic power steering system, it is going to use a servo motor with a potentiometer on at the steering column. Okay, and if you are using a if the manufacturer is providing a hydraulic power steering system, then it is going to use a hydraulic actuator. Okay, so now let's talk about Tinkercad. So have you ever heard about this thing, Tinkercad? Yeah, guys. I think this is a new term for you. So Tinkercad is a browser-based software which allows you to create control systems. So it is a basic software. I'm gonna show you the layout. Yeah, I hope my screen is visible.
Yes, sir.
Yeah, so this is a free software. It is like you don't need to download it or something. You can just you can just search for Tinkercad on Google and open the site, register your email ID, or just like link your email ID with it, and you can create certain circuits. It has got various components like resistor, LED, push button, slider switch, potentiometer, batteries, Arduino, transistors, and various such things. There are other components as well. There are other photo diode, there is photoresistor, then there is a temperature sensor, ultrasonic sensor, We also have a humidity sensor in this. Okay, so all you need to do is drag and drop in this workspace, and you have to you need to connect those parts and write down a code if you want to. If you don't, if you just want to create an electrical circuit, you can also do that. Okay, this is an electronic circuit because we are using a microcontroller, a sensor, and an actuator. So this is a circuit which is used to control the speed of a servo motor using a potentiometer and an Arduino. So I've written a code over here which says that for the first in the first line we are saying that servo ESC, like firstly we include the servo library. So if you have ever used C language, then you must be aware about the very first two lines are hashtag include stdio.h, then there is a conio.h, then there is match.h if you want to perform algebraic equations or differential equations. So there are certain libraries for Arduinos as well, and the language is similar to the C language. Okay, so initially we include the servo library, then we term the servo motor as ESC. Okay, then we assign an integer value as pot value. So this pot value is potentiometer value. This is the potentiometer over here. So the value of this pot value is coming in the form of an integer. Okay, and we are we later are going to assign a particular pin to it. Okay, so first and foremost we start the void setup. So for every code for Arduino, there are two loops or the two setups. So one is the void setup, like two sections of code. One is the void setup and other is the void loop. So void setup is something that where we assign something to the microcontroller, like tell something that at this pin we have such part connected with you. Okay, like for example in this one we are telling the microcontroller that ESC is attached on pin 9 and its maximum pulse width is 2000 milliseconds while microseconds, while its minimum pulse width is 1000 microseconds. Okay, then we start the void loop. In void loop, so this void loop, as the name says, it says loop, it runs this code in a loop. It continuously will run this three lines in a loop. Okay, so in void loop we first assign that the pot value is an analog value or an analog read for pin A0. Okay, so this A0, you can see that the center terminal or the middle terminal of the potentiometer is connected to pin A0. And as we know, A0 is an analog pin and the output of potentiometer is also an analog signal. So that's why we are connecting it with A0. Okay, then we are saying telling the Arduino to map the value of this pot value to from 0 to 1023 to 0 to 180. Okay, so what we are doing here is that we are scaling down the input value. So this output values of potentiometer will be scaled down from 0 to 1023 to 0 to 180. Okay, so this 1023, you might be asking like why is it 1023? So it is a value for Arduino that considers 1023 as 5 volts. Okay, so to scale it down, there is a formula, or else you can just assign it like this. And then lastly, we tell the microcontroller to write that particular value to the to convert the value into a PWM signal and send it to the servo motor. Okay, so let's start the simulation. So you can see that as I rotate the potentiometer, the servo motor is going to rotate. Okay, you don't like for because of this Tinkercad, you don't need to buy any new products or buy any components from online or from your market and then write the code connect each and everything and do it. You can use Tinkercad and bring in all the parts, and this is for simulating your projects. Okay, so this particular type of system or control system, like using potentiometer and servo motor, you can make throttle by wire or ride by wire or drive by wire. All the three names is same. You can also make steering by wire or electronic power steering system. Then you can also make brake by wire. You can make you name it, you can make many things out of this. I use this particular system for my steering system of my skill model car. I was trying to implement CAN protocol on a skill model car. So I had two potentiometers on one end and there was a DC motor and a servo motor on other end, and both the motors were just controlled by two wires. There were not, like you can see, there are these many wires in just one system. So I reduced it down to add three Arduinos that would be able to control each other, like communicate with each other, and the data would be transmitted through just two wires. So this is a basic example of throttle by wire, brake by wire, drive by wire, or ride by wire, and steering by wire. Okay, now let's talk about controlling the speed of a DC motor. So this is a DC motor, and the functioning of DC and AC motor is almost similar, but only DC voltage is applied to this particular motor, which it actually converts into an alternating current. Okay, the fundamental of it, I'm not going to talk about why it is doing so or why am I saying so. It is all because of electromagnetism, and DC voltage cannot produce electromagnetic fields. It is just the AC voltage that can create electromagnetic fields. Okay, so we have a transistor, a capacitor to convert a PWM signal or a digital signal into a voltage value. So again, we have a potentiometer which is connected with A0. Then we have pin 11 or 12, I guess, yeah, 12 with the center portion of this transistor. So it is connected with base. Okay, there is emitter, collector, and base. So this one is going to give the signal to a transistor to switch on or switch off the voltage. Okay, then we have a capacitor to drive the current in both positive and negative. So this is the code. It is a simple code, and you can you can use the same code. You can change this code for certain things. And to start the simulation, like when we start the simulation, you can see as soon as I rotate the potentiometer, the speed of the DC motor is going to change. Now this particular code has some bug in it, because after a certain point, it will either go to zero or it will go to its maximum speed. So there is some bug in this code. I'm trying to resolve it, but I haven't yet. So, but I hope you are understanding how potentiometer can be used to control a DC motor as well. So this is in simple way. This is an example of your traction motor, or even your fan, your ceiling fan or your wall mounted fan. Okay, so you can use Tinkercad to create or to even to simulate your projects, and then you can finally order those parts and connect them physically, then copy the same code into that microcontroller and run it. So this is the software portion, and you can then implement the same thing on the hardware portion as well. I hope you understand Tinkercad as well. So that was it from my end. If you have any queries, you can ask me right now. Yeah, guys. You guys have any queries?
No, sir.
Okay, if not today, if whenever you have any query, you can contact me on my email ID as well. Even your faculty has my phone number, so you can contact me through my phone number as well. You can ask for my phone number from your faculty, and you can check out my YouTube channel for more such videos. Like I have videos explaining the electronics portion of engine, just the basics of automotive electronics. Then there are various videos for various automotive systems like suspension, steering, brakes, and many more. Transmission, powertrain, and you can also check out my book, Engine in a Nutshell. This book is focusing on the electronics portion of engine. I have covered electronic fuel injection system, electronic spark ignition system, even what is fuel map, and how that fuel map is used by microcontroller to control the fuel supply to based on the engine speed and the load on engine. And so technically I know like this book is based on Kirpal Singh, but Kirpal Singh has not covered a lot of electronics portion. So this book is only focused on electronics of engines. Okay, so this is it for our session. If you ever have any queries, you know where to contact me. And I hope you understood today. I hope you understood what I taught today.
Yes, sir.
Yes, sir.
Good. So I also has anyone of you, like, has anyone from your class participated in that event of go-kart, organized by ISI India, Indian karting race?
Yes, sir.
So I think we would have met there, right?
Yes, sir.
Yeah, I do remember meeting your college's team, and you guys performed well in the tug of war event. And I'm hoping that you guys will make two carts in the next season, one for IC engine, another for electric cart. And on a serious note, if you participate in the electrical cart competition, you will understood how an electric vehicle or how an electric vehicle is built, and you will be able to, like, there are motor controllers and battery management systems available in market which you can just plug and play. But initially you can use them, but with time you can also try and develop those systems for your particular car. And also you can if you don't want to participate in those kind of events, you can always create a scale model car. So you can just create a scale model electric vehicle as well. Just control a DC motor, servo motor, and have them steer your car and give the speed to your car. Okay. So,
Yes, sir.
yeah, I hope today's session was interesting. I'm gonna ask Shiv Kumar to please grab the attendance, and I don't think so faculty is available. Joshi sir is not available, right? Yeah. Okay, Shiv Kumar, please.
Yes, I'm taking the attendance.
Okay. Thank you. So I think I'm gonna leave the meeting now.
Sure, sir. And I request all the participants to please put their roll numbers in the chat so that I could copy them.
Okay. Yeah, Samat was saying something. Okay, Shiv Kumar, you can grab the attendance. And thank you guys for attending today's session. I hope you had fun and I hope you learned something. And I seriously want you guys to implement these things for your future projects. Okay, thank you guys for having me here.
Thank you, sir.
Thank you so much, sir.
Thank you so much, sir.
Yeah, thank you. And have a good day. Bye.